Hi, welcome to our software simulations project on internal combustion engine components.
Hello, my name is Torres. I am a mechanical engineer major. My motivation to be a mechanical engineer was from my dad and my grandpa. I just followed them, and I had a very good ability at math. Uh, my primary hobbies are involve motorsports and the gym. I track a motorcycle, and I try to do it at least once a month, but sometimes it doesn't happen. And and I go to the gym every single day.
Hi, my name is Jeremy Valdes. I am a junior mechanical engineering major, 1 year away from graduation. While I'm not studying, I enjoy spending time working on boats and fishing. Occasionally, you may also see me in the golf course.
Hi, my name is Jason Rodriguez and I'm in my junior year for my bachelor's degree in mechanical engineering. Besides studying for classes, I enjoy watching motorsport series such as Formula One or NASCAR and IndyCar, and some hobbies include just working on my truck and attending local motorsport events. As for the introduction of the project, engines have been around since the late 1800s, but even with innovation in the past 145 years, parts are still susceptible to damage, so we will cover the external load effects on each component. As for the simulation settings, we went with a solid standard default mesh for all studies. The piston material is a 2024 aluminum alloy. The piston pin is a steel alloy. Connecting rod is also 2024 aluminum alloy. The crankshaft and the engine block are both steel alloys. Pistons are one of the more valuable parts in an engine since they are responsible for the compression of intake gases, fuel, and capturing the energy from the fuel blast. For this study, a 120 psi pressure load seemed appropriate. With this and the piston being fixed on the bottom face while a pin connection was applied through the piston, it showcased that the piston head does not yield and meets our factor of safety goal of at least 2. It does this while maintaining minimal displacement, strain, and stress.
This analysis shows the piston pin safely handles both bending and shear force from peak combustion forces simulated with a 6,500 Newton load. We used a steel alloy which showed no yielding and exceeded our factor of safety requirements. The results confirm that the design is structurally sound and our assumptions for material and loading are accurate. This analysis evaluates the crankshaft under combined bending and torsional loading during the power stroke. A 6,500 Newton force and 1,000 Newton meters of torque were applied to simulate combustion and rotation. The bending results showed minimal stress with a very high factor of safety of 120. However, torsional loading was more critical with a factor of safety of 13. This indicates the current design may need reinforcement or stronger material for long-term reliability.
Connecting rod is primarily designed to go through axial loads, one being the compression load. When the piston is in its power stroke, when gas is injected into the engine and then combusts with the spark, there is very high pressure created on the piston head and the top of the connecting rod. Due to this high pressure, the amount of compression force can be in hundreds if not thousands. For this study, we will be using 30,000 newtons on the inner top part of the connecting rod and fixing the inner bottom to simulate the compression of the connecting rod at this stage. Although the connecting rod is primarily designed to undergo axial loads, it also receives high bending stresses. The bending stresses occur due to the angular movement that the rod does while the crankshaft is also rotating. This will happen when the engine is on its midstroke, where the angle between the rod and the crankshaft is at its largest point, leading to so much stress that could be fatigue failures. For this study, we used 5,000 newtons to simulate. When the rod is under its most extreme compressive loads, primarily when the engine is at its maximum performance for a very long period of time, the rod is at risk of buckling. Buckling is a type of failure that happens when the structural member is subjected to a very high compressive force, which is what the rod mainly experiences. This makes the rod's design very concerning, so it has to be very thought out and very carefully designed. They use a bunch of studies and check a bunch of things, like the geometry, the slenderness, the end conditions, and the Euler buckling theory as well. We used 30,000 newtons to simulate this study. To run a case study on the connecting rod to the nature of how the engine components work together. Usually connecting rods take the most abuse besides piston heads since they deal with constant compression and rotation at their bearing points. With this in mind, we determined that the connecting rod holes that connect to the crankshaft and the piston pin were ideal places to analyze. We also checked for 3 different materials, 2024 aluminum alloy steel, and the 7075 T6 SN aluminum, which is widely used throughout engine components. From the optimal results, it is concluded that the top hole should be reduced to 34 millimeters, while the bottom hole should be increased to 50.1 millimeters. The optimal material is a 2024 aluminum alloy at a mass of 438.31 grams. These changes come with the optimal stress of 162.6 megapascals, a factor safety of 3.488, which means the design criteria and does not yield.
Piston thermal analysis, both steady-state and transient cases were studied. While the steady-state case represents the engine running for long periods of time with stabilized temperatures, the transient case reflects thermal loads over long periods of time when you turn on your car. For this case, the piston head was initially at room temperature, while the thermal loads were applied through a 2-minute time period, and in this case with 30-second intervals. While both studies were illustrated with gradual temperature gradients, with the hottest points being at the top of the piston and the coldest at the bottom, the temperature difference across the parts were drastic, with a 5-degree difference for steady state and a 40-degree difference for transient. However, there were some abnormality spikes throughout the transient case at the bottom of the piston head, which could result from geometry or material density. Here's a figure showing direct comparisons between the two cases, with the graph detailing the temperature difference across the piston from top to bottom. One thing in particular that was interesting with the aluminum piston head was that it yields to thermal stress, but this can be resolved with a simple change in material. Thank you for watching.